Hello, AP Chem. Today we're going to do our second day of notes here in chapter 18. So this will be 18-2. We are talking still about spontaneity here. And we know that a reaction is said to be spontaneous if it does occur at a given set of conditions. What we want to do is we want to kind of get this connection between spontaneity and entropy. What does spontaneity really mean? And why, when is it favorable and what does that mean? So first, we're going to look at the second law of thermodynamics. For all spontaneous processes, the entropy of the universe increases. So that is what makes it spontaneous, is really what's going on is the entropy of the universe is increasing. And so that's making the reaction spontaneous. So we're going to use positive delta S for the universe. And if you add up the delta S of the system and the delta S of the surroundings, you're going to get the delta S of the universe. So you can just add up all your entropy of the system and the surroundings. So first, let's just look at how does the reaction affect the delta H of the surroundings. So if a reaction is kind of the connection between the system and the surroundings. So if a reaction is exothermic, obviously we know that's a negative delta H for the system. We know that the reaction releases heat to the surroundings. And that's what we're showing here with this little diagram. Here's your system in the flask. It's releasing heat, so we know it's an exothermic reaction. So when a reaction releases heat, obviously the temperature increases for the surroundings, right? Because the reaction released heat. And so that is a positive delta S for the surroundings. So what we're saying is if we have a negative delta H of the system, that's going to give you a positive delta S of the surroundings. So basically an endothermic reaction is going to release heat and make the surroundings get more disordered, right? Increase entropy, more disordered. So that's really what's making an exothermic reaction favorable, is that it's making the surroundings a positive entropy. All right, so the opposite, obviously, for an endothermic reaction. So when we take a look at an endothermic reaction, we have a positive delta S for the system. So the system absorbs heat from the surroundings. So when the temperature then is going to decrease, because the system's absorbing heat, the temperature decreases for the surroundings, and so we have a negative delta S of the surroundings, right? So when we have a positive delta H of the system, we're going to have a negative delta S of the surroundings. So that's going to be unfavorable, right? Unfavorable. And this is really why an endothermic reaction is unfavorable, is because it's making the surroundings less disordered. And so that's unfavorable. Okay, so that's really the driving force as to why exothermic is a favorable change and endothermic is not. Okay, so now we're going to derive this concept of Gibbs free energy. So it stands for delta G, Gibbs free energy. And again, it's really related to the delta S of the surroundings and the universe. So if we say the delta S of the surrounding is negative delta H of divided by temperature, which is really what it is. We saw this connection when you had a negative delta H, you had a positive delta S. We're going to divide it by temperature just to keep the situation really equal. But it has to do with exothermic is going to be a positive delta S to the surroundings. So we are going to plug this definition into our delta S of surroundings there. And then we are going to multiply by T well, we're going to plug that in. Let's plug that in first. So delta S of the universe is equal to delta S of the system. And then we're going to plug in our negative delta H over T for the delta S of the surroundings. And now we're going to get rid of the T out of the bottom here. So I'm just going to multiply the whole thing by T. Actually, let's do negative T. And what that does is then when we distribute that out, we're going to get negative T times the delta S of the universe is equal to, I'm just going to move this term around here. So we have delta H, and then we're multiplying by T here. So minus T of the delta S of the system. Do you see what I did there? I just moved the delta H around. So that is our equation. And now what we're going to do is we're going to define this, the negative T times the delta S of the universe, to be delta G. So that's really going to be our spontaneity. It has to do with how the change in entropy of the universe changes. We multiply by temperature. And so that's going to equal delta H minus T delta S. And when we write the equation this way, this is the equation, it is on your reference charts. When you write your equation like that, we always need everything of the system, right? So this is the delta G of the system, this is the delta H of the system, and this is the delta S of the system. So we've changed everything so it's for the system. And the concept that we want to start getting is that delta G, which we've talked about before, is really the energy available to do work. Okay? And there's a couple of things we want to think about. What's going to happen is we're going to get this situation where when we have a negative delta G, it's going to be spontaneous. When we have delta G equal to 0, we're going to be at equilibrium. And when we have a positive delta G, then we know we are non-spontaneous. And this really just comes about as far as making this delta G. We want to make our delta S of the universe positive, right? And so that's why we're going to end up with a negative delta G to be spontaneous, right? So when you have a positive delta S of the universe, you're going to end up with a negative delta G. So that's going to be spontaneous when you have a positive delta S of the universe. Okay, so if we want to just think of it that way, as far as it being favorable for making the universe more disordered. Okay, let's move down here. We are going to look now. We obviously have this equation. This is an important equation. We're going to plug into it all the time. We have the delta H and the delta S of the systems both affect our delta G. So we want to look at all those different situations. So the easiest one to look at is if we have a positive delta S, which we know is favored, and we have a negative delta H, which is XO, which we know is favored. What's going to happen is we're going to come out to be a negative delta G. So, you know, you can just plug in, let's do it this way. Delta G, oh, that's not good. Okay, sorry about that. Let's do that again. So we were saying the delta G, we want it to come out favorable, spontaneous. So in this case, if we have negative delta H, I can kind of plug in like a negative delta H and then minus a T with a positive delta S. Obviously, you can see with this situation, it's always going to come out as a negative delta G, right? It has to come out negative in that situation. So that means this situation, I'm sorry, it's going down there a little bit, is always spontaneous. So what we're saying is both driving forces, the delta H is XO, which is favored, and the delta S is favored, which is positive, right? Positive delta S, more entropy, that one is favored. And then also exothermic is favored. So it's always got to be spontaneous because both driving forces are favored. So the opposite scenario is when we have a positive delta S, which is endo. So what's going to happen with our delta G, we're going to have a positive delta H minus a T, and now our negative delta S. So what we're saying is both driving forces are not favored. We have endothermic, which is not favored, and we have negative delta S, less disorder, that is also not favored. So this is going to never be spontaneous, right? Always non-spontaneous, never spontaneous, no matter what your conditions. Okay, so those are the extremes. And then the other two are going to be the scenarios where sometimes you can get it to be spontaneous and sometimes not. It depends on the temperature. So let's look at this scenario here. If we have our delta G, we're going to have a positive delta H and then minus T, and now our delta S is a positive delta S. So you can see that if we want the delta G to come out negative, we need like a bigger temperature so that we really have a bigger negative there to get our delta G to come out to be negative. So one way to think about this is kind of the T delta S factor needs to be a bigger factor. So I'm going to write that as T delta S, and I'm just going to make that absolute value has to be greater than the absolute value of the delta H. So, if the magnitude of the T delta S is bigger, that's going to make our delta G come out negative, right? So we need a high temperature here to make this a bigger value. So this is going to be spontaneous at higher temperatures. Okay, so it's not always spontaneous, but it's kind of like the part that's favored is the delta S. So we want to make this T delta S factor as big as possible to get it to become a negative delta G. And then we're going to have the opposite here for a negative delta H and a negative delta S. So delta G is our negative delta H minus T with a negative delta S. So in this scenario, once you distribute your negative here, your T delta S kind of comes out as a positive value overall. And so we want to make this T as small as possible to make it come out spontaneous. So we're going to want our delta H to be the bigger factor, right? Because that's our negative delta H. That's our favorable scenario. So that's going to be bigger than our T delta S. And again, I'm just using absolute value to do the magnitudes of them. So in this case, we want to make the T delta S factor the smaller factor. So we're going to be spontaneous at lower temperatures. Okay? So again, these two just depend on the temperature. The others are either spontaneous or non-spontaneous. Okay, so one thing I want to point out, the examples where they depend, right? And that's going to be this one, and it's going to be this one. These are the ones that depend on the temperature. Those are the examples that I have down here. So this example number one is a scenario where I have a negative delta H, and I have a negative delta S. Now, how did I know it was a negative delta H? This is a simple phase change. I'm going from liquid to solid, which means I'm making bonds. And if you remember, making bonds is a favorable change, right? So it should be exothermic. It's favorable. So that's how I know that going liquid to solid, I know I'm making bonds, and so I know it's a negative delta H. Now, what about the entropy? Going liquid to solid, obviously you're getting less disordered, more ordered, which is a negative delta S. So we're saying less disordered because liquid to solid. Okay, so obviously that is unfavorable in terms of entropy. And that's exactly the scenario that we're describing here, where it's only spontaneous at lower temperatures. Well, is that true? When you go liquid to solid, you need to freeze. Yeah, freezing happens at a lower temperature. So it's all because you need it to get less disordered, and so that's why you need that lower temperature. It's going to be the opposite for this example over here. Here we're going solid to liquid. So in this scenario, we have a positive delta H, and it's because you're going solid to liquid, which you know that you are breaking bonds. And so please remember you're pulling those apart. So that's going to be, it's going to take some energy to do that. That's going to be your unfavorable change. You have to kind of pull them apart. Then your positive delta S, you're going solid to liquid, so it's getting more disordered. So that makes sense that that should be a favorable change. And so again, this is the scenario that is described when you need it's spontaneous only at higher temperatures. So this is melting, you're going solid to liquid, you're going to need to break bonds, you're going to do that at a higher temperature, right? So obviously, you know, freezing happens at a lower temperature and melting happens at the higher temperatures. And so those are scenarios where you have one driving force is favorable and one is not. And so they depend on temperature. Okay, so that's kind of a rundown of the kind of overview of all this different scenarios there. All right, so now I'm going to scroll. Let's go down to the next page, flip to the next page. And now we're going to do some calculations. So there's a couple of little things. So there is what's called a delta G naught with that little circle at the top there. That is officially the standard free energy change. And it's the same thing as delta G, except that you're doing it at standard conditions. And the standard conditions is at 1 atmosphere and 1 molar solutions for any solutions that you have. So this just kind of standardizes it so that we're all at the same conditions, because the spontaneity will change with different conditions. So for right now, we're going to keep things easy and always keep it 1 atmosphere and 1 molar. So we can use the same equation, our delta G equals delta H minus T delta S, but we're just going to put the knots in there. So it still works the same as long as everything is at standard conditions. You still have that same equation, and that's on your reference chart. So this chart here is kind of giving us this one scenario where it's like at the freezing, you're freezing from solid to liquid, and we're kind of looking at the delta G and seeing when that is favorable. So again, this is at 1 atmosphere pressure, so that is at standard conditions. And we're just looking at the different temperatures and whether it's spontaneous or not. So we know freezing needs, oh, I am so sorry. We are not freezing. We are melting. You're probably wondering what I'm doing. Solid to liquid, we are melting. So melting, obviously, it should be spontaneous when it's at warmer temperatures. So this chart looks confusing, but it's basically looking at, well, what's the delta G at negative 10 degrees? What's the delta G at 0? What's the delta G at 10 degrees Celsius? And you can see that the delta S, oh, I'm sorry, the delta H is a positive delta H, and so it's unfavorable for delta H, and that's because we're breaking the bonds. And then the delta S is favorable. It's got a positive delta S, and that's because we're going solid to liquid. So obviously, when you plug in a negative 10 degrees Celsius, you're coming out with a positive delta G naught, which means it is it's non-spontaneous, because you have a positive delta G, so it won't occur at negative 10 degrees. It's not going to melt. At 0, you're right at 0 because you're at equilibrium. You're right at the freezing point. at the melting point. At the freezing point, it's the same point. So you're at equilibrium. And then obviously at 10 degrees, we're above that melting point. It is definitely going to melt, so it is spontaneous at 10 degrees. So that's kind of just giving us the same idea, just doing it with delta G naught. So all freezing points and melting points and boiling points should have a delta G equal to 0 when they're at that melting point or freezing point, because they're at equilibrium. All right, let's move on here and look at this example here. Some of the kind of questions now, we're just going to kind of plug into the equations and solve for what we need. So this first one is a typical example. We have calcium carbonate solid, and it decomposes into calcium oxide and CO2 gas. We're just looking for the delta G naught. And so obviously to find the delta G naught, we need to know what the delta H is, what the delta S is, and then we can use our delta G equals delta H minus T delta S. So you're going to have to do some calculations. So you might have to use your heats of formations and look them up in the appendix, or maybe it's given to you to solve for your delta H of the reaction. So products minus reactants, I have already done that. And so that's our delta H of the reaction, which is positive. And then we have our delta S, where we need to also look up those values, do products minus reactants for the entropy, and I have already calculated that. And so now all we have to do is plug in. And remember, all the values you're getting off the charts are always the standard entropies and the standard heats of formation. So we are going to plug in, and here we go. So the delta H naught is our 177.8 kilojoules per mole, minus our temperature in this case. It said we're at 25 degrees Celsius, so we're at 298 K. And then our delta S is our 160. Now be careful. This is kilojoules, this is joules. We need to change them to be consistent. I'm going to change this to kilojoules, so 0.1605 kilojoules per Kelvin moles. And I think that looks pretty good. If you calculate that out, you should get a delta G naught equal to 130 kilojoules per mole. Okay, the kelvins cancel out. So that is our delta G naught. So those are very straightforward questions where you just plug in to our delta G equals delta H minus T delta S. Now, sometimes those were all at standard conditions, and at 25 degrees Celsius is also a standard condition. So now what we're going to do is we're going to change the temperature, and what this does is we're trying to figure out at what temperature the reaction becomes spontaneous at standard conditions. Now, when I say standard conditions, we're not going to include temperature as a standard condition. So the standard conditions are the 1 atmosphere and the 1 molar. But before we were at 25. So now we're going to change our temperature. We want to know at what temperature does it become spontaneous. So when it changes from non-spontaneous to spontaneous, you are right switching from positive delta G to negative delta G. So we want to set our delta G equal to 0 because that is right where you're at equilibrium. Because you need temperature at equilibrium. All right. So when it's at equilibrium, we want that temperature because that's where it's changes from non-spontaneous to spontaneous. Okay? All right. So if you ever want to know what temperature at which it's going to turn spontaneous, always set your delta G equal to 0. So now we're going to plug in, so into delta G equals delta H minus T delta S. So we get 0 equals our delta H minus our T delta S. In this question, we're looking for temperature. So I'm going to rearrange and solve for temperature. So T delta S is equal to our what did I do? T delta S is equal to delta H. And now I'm going to divide by temperature. So let's just move that over there. Oh, no, let's do it the other way. Sorry. T delta S. All right, so I have my temperature here. I'm going to get rid of my delta S, and we're going to put that here because we're going to try to solve for temperature. Okay, sorry about that. All right, temperature equals delta H over delta S. We're looking for temperature. Let's just plug in. Here we go. Delta H was our 177.8 kilojoules per mole. And then we divide by our 0.1605 kilojoules per Kelvin moles. And that's going to come out in Kelvin, 1108 Kelvin. You can leave it in Kelvin, or if you want to change it, I believe it's 835 degrees Celsius. So that is the temperature at which it would become spontaneous. Now, in this case, our delta S is positive, which is the favored driving force. So it would be that temperature or warmer. It's just above 835 degrees Celsius. It's going to be spontaneous. So above 835 degrees Celsius, it is spontaneous. Because the warmer it is, the more spontaneous that reaction is going to get. Phew, okay, so we're almost there. This one has a phase transitions, kind of similar to what we did up above. So we can figure out a few things. So in this question, we are going bromine liquid to bromine gas. What is the boiling point? And again, the boiling point, and it's at standard conditions, 1 atmosphere. The boiling point, again, is when it has to be at equilibrium. So we know the delta H, we know the delta S. We are going to set our delta G equal to 0 because we are at the boiling point. Because at the boiling point, which again is at equilibrium. So we're going to set our delta G equal to 0. So that means 0 equals our delta H minus our T delta S. We are looking for our temperature again. So temperature is our delta H over delta S. Now in this case, the delta H is the delta H of vaporization because it's that's what it's doing. It's going from liquid to gas, which is vaporization, but it's just our delta H. So we're going to plug in 31.0 kilojoules per mole divided by, I'm going to change that to kilojoules, so we're going to get 0.0930 kilojoules per Kelvin moles. Calculate that, and you get 333 Kelvin. Okay, so this one again also has a positive delta S, and so again above that temperature, above 333 K, it is spontaneous, which again makes sense. You are boiling, so as you get hotter and hotter, obviously it's going to be, when it's above the boiling point, it's going to be spontaneous. All right, last but not least, you can also calculate delta G naught, kind of doing like what we did with delta H and delta S, where we can take the delta G of formation and do products minus reactants. So this delta G sub F here, that is the standard free energy of formation. So it's just like the delta H of formation, but it's a delta G of formation. So it's the free energy change that occurs when 1 mole of a compound is synthesized from its elements in the standard states. So the delta G of formation of CO2 would be for the reaction of carbon as graphite plus O2 goes to CO2. So that delta G naught for this reaction from its elements to that compound. So it's exactly like delta H of formation, except it's delta G of formation. So again, those are going to be in our appendix 3 that we have posted for you. And you just do products minus reactants. So here I'm giving you your delta G of formations. And you can just plug those all in. So let's just do this one really carefully. So we're going to do delta G naught, and so this is for the full reaction, right? Is going to be our products minus reactants. So our products in this case are our CO2 and our water, and we need 3, 4 there. So our CO2 is the negative 394.4. So we're going to do brackets 3 times the negative 394.4 plus the 4 times the water as a liquid. Make sure you do check your states as we've done before. And then, so products minus reactants. In this case, we have C3H8. That is our, there's only one of them, negative 23.47. And now we also have oxygen, which is a pure element. So just like delta H, that's going to be equal to 0. So plus 5 times 0. So all pure elements in their standards, in their most stable state, are going to have a value of a delta G equal to 0 for that pure element. So now we just have to solve, and we are almost done. I got negative 2252.2 kilojoules per mole. So sorry that was a little bit long. Hopefully wasn't too painful. Thanks a lot.